Is it started?
Yes, sir.
Okay. Yeah. Sure. So I should start
Yes, sir.
discussing this. Okay. Hi. Welcome. So we are in the second live session of this course matrix solvers, and in between there has been a technical problem. Most of you probably have noticed that in the 9th week few videos are not uploaded properly, and those were the introduction to Krylov Subspace, and later videos, the later tutorials which are conjugate gradient and GMREs has a dependency on those videos. So though it is a technical error, but on behalf of my team I also apologize for this inconvenience. However, the new the right videos have been uploaded already. So in the and you can start looking into those videos as well as the lecture material on Krylov Subspace, introduction to Krylov Subspace, and start building your understanding on conjugate gradient GMREs followed by pi conjugate gradient solvers. And in 11th week we have been discussing about the preconditioner and multigrid systems. So which also in some way also related with this 9th 10th weeks lectures, which are Krylov subspace based methods. So I thought it will be important at this stage, because there has been some interruption in the flow of the lectures due to this technical problem. If we meet once via this live session, and if you have any questions specific to particularly that part, like introduction to Krylov subspace and its follow up as conjugate gradient and GMREs, we can probably discuss that. On top of that, I remember we last time the live session was done when lecture up to week 6 or week 7's lecture were done. So we have just finished the direct solvers by that time and eigenvalues, etc. And now we started discussing the iterative solvers, and a number of iterative solvers we have discussed. We started discussion with basic iterative solvers like Gauss-Seidel, Jacobi, SOR, and then we discussed about projection based iterative solvers, steepest descent on minimum residual, and now the later discussion followed as Krylov subspace. So if any question regarding this particular part, the iterative solvers and the foundation of the iterative solvers are there, I will also try to answer this. I got a few questions from the Google form that has been supplied to you. The first one is from Madam Kalpana. I need example for transpose of a symmetric matrix need not be symmetric. The basic definition of a transpose of a symmetric matrix is, where is that? Is that a basic definition of a symmetric matrix is that its transpose is equal to that matrix. So if a matrix is symmetric, its transpose will be equal to that particular matrix, it will be symmetric also. So transpose of a symmetric matrix cannot be asymmetric. Cannot have, so this there is no example on that. You can for example, you can take a transpose a symmetric matrix and try to find its transpose. It will see you can do it taking a 2 by 2, 3 by 3, 4 by 4 matrix and can find it yourself. There is another type of matrix which we should probably quickly discuss, which are called skew symmetric matrix, which is Aij is equal to minus Aj. So the matrix has a row column combination which is negative of that column row combination, and transpose of the skew symmetric matrix you can also see it is also a skew symmetric matrix. So in also in that case, if B is skew symmetric, B transpose is also so. So the symmetricity as skew symmetricity is a property which will be conserved in transpose. I did not understand the question from Roshan Mishra. Himanshu Shekhar asks explain decoupling a system. I am not sure about which particular thing you are asking, which particular field you are asking of decoupling a system, but if we can take a what is a decoupled system, when one system has no dependence on the other system. So, if we have a system of equations, say A11 x1 plus A12 x2 is equal to B1, A21 x1 plus A22 x2 is equal to B2, this will be a coupled system, as x1 and x2 are related by the equations. Now, but now if I can diagonalize this system, so I have a matrix Ax is equal to B, and this A is basically A11, A12, A21, A22. Now, if I do certain row operation called row combination, division, etc., and then I get say dx is equal to B. D after some operation, so I will do subtract A11 multiplied with A11 divided by A21 and multiply again, multiply the first row by A21 by A11 and subtract from the second row. So, I will get A11, A12, I'll 0 and A22 minus A12, A21, A12, and then I multiply this term by A12 and subtract it here. So, I will get something that this matrix will be say D11 and A22 minus whatever is there A12, A21, A12. So, the entire system will be a diagonalized system of equation. So, the equations will be D11 x1 is equal to, this is B prime, B prime 1, D22 x2 is equal to B prime 2, and this will be a decoupled system. This is a coupled system because x1 and x2 both are required to write down this particular equation. Here only x1 can write this particular equation. So, this is a decoupled system. So, from matrix point of view, if we consider diagonalization of a system of equation, we will get a decoupled system of equation. The third one is from Suresh regarding something on gate lectures in electrical, which I did not understand. Similarly, the question from Amit Kumar Srivastava is also not complete. Amit Singh asks how matrix solutions can be customized. And I have a confusion regarding what are you exactly meaning by the term customization, but if we can see that in matrix solution there can be in general two different classes. Matrix solutions, there can be in general two different techniques. One is that direct solution, that means no guess is needed. You directly find out solution of the equations, and here are some classes like Gauss elimination, LU, Kramer's rule. One particular case may be there can be keyword decomposition, one particular case may be TDMA, etc. So, in this is only applicable for tridiagonal matrix. So, depending on how is your matrix, how can you decompose it, can you quickly get an LR form or QR form, can you quickly find out the determinant of the matrix if you have already upper triangular or lower triangular form, so that you can use it early, you can find out your matrix solutions. The other class is which we are discussing right now is the class called iterative methods. The general problem with TDMA with the direct solvers except TDMA, that the number of operations are very high, which is of the order of n cube. Of if n by n matrix, the number of operations are n cube. However, In iterative solvers, though we do not solve it, we start with a guess value of solution and update it. So, there is a class of thought which tells that iterative solutions is a method which has been proposed by in ancient Indian mathematics texts. Iterative, you find out a solution and you find out an error and you try to reduce the error, you try to find out the ether part of the error, you reduce the error, minimize the error and then you get it. So, you try with a solution and update the guess solution so that the error is minimized. And this iterative methods has broadly one class which is called basic iterative method, where you have GS, Jacobi, SOR. The restriction is that this is only for diagonally dominant or irreducibly diagonally dominant systems. There is another class which is called projection based method. They start with a guess value, they find out the error, project the error with respect to some space and try to minimize it. And the first group is 1D projection and the other one is multidirectional projection, or what we are doing, Krylov subspace methods. In 1D projection, your steepest descent, minimum residual, all these things comes, and in Krylov subspace conjugate gradient, BiCG, GMRES etc. comes. So, these are the broad classification of matrix solvers. And now, how to choose a matrix solver? If you have less number of rows and columns, smaller equation system, you can probably go for a direct solution method, where this number n cube, you have 100 by 100 method, n cube is 10 to the power 6, which is a relatively small number, considering that you now have gigaflop or petaflop computing system. 10 to the power 6 floating point operation will be done in seconds. So, you can choose something like Gauss elimination. If you have a tridiagonal matrix, you can essentially choose TDMA, which is a very fast method for tridiagonal matrix. You have a lower triangular matrix, or you have a matrix whose lower triangular and upper triangularization is already given, you can choose LU method. If you have a sparse matrix which is large in size, you may not choose any of these, you can come to the basic iterative methods. If you do not want to do very complicated mathematics, but write a simple back of the envelope type of calculation, few lines of code to solve a method, you can choose GS, Jacobi, SOR if the matrix is diagonally dominant. If it is not, then you have to go for the projection based methods. Again, if it is a symmetric matrix, you can choose something like a conjugate gradient method, which gives you first result. If it is a non-symmetric matrix, you have to choose something BiCG or GMRES to solve it. So, depending on what type of matrix is that, what is the size of matrix, is the matrix sparse, is the matrix tridiagonal, depending on all these facts, you choose your particular matrix solver. On top of that, there will be some other techniques to customize the matrix solver. That means, you already have a, I am using the term Amit Singh has used, customization of matrix solver. It's the scientific term is of course not customization. So, you already have a matrix solver, how to get faster solution. You have Gauss Seidel, you use an over relaxation factor, or say that you are using successive over relaxation SOR to get fast solution. You have conjugate gradient or BiCG or GMRES, you right now cannot use something like a SOR or over relaxation technique to get faster solution, but then also you can use preconditioning technique or multigrid, which we are discussing right now. So, that in preconditioning technique, the condition number, you multiply something with the matrix instead of solving. So, we look into preconditioners, preconditioning. Say I am using GMRES to solve a matrix equation. I have my initial equation Ax is equal to b. A has high condition number, and we can see that the number of steps required for GMRES to converge will be large if the condition number of A is high. So, what we will do, we will multiply a matrix M inverse in the both side of that. So, yeah, my new equation is M inverse A x is equal to M inverse B. So, that M inverse A has smaller condition number. And how this is done, that is a question. M inverse, we say that we will, if M inverse is A inverse, if some way I can find out A inverse and multiply with A. So, I will have x is equal to A inverse B. A inverse is somehow explicitly calculated. I can solve it in a step. I do not need actually GMRES or anything to solve it. It is what we are calling about a decoupled diagonal system, and we can directly solve it. So, because and we can solve it because A inverse A is an identity matrix which has condition number 1, lowest condition number. So, if I can find M inverse is close to A inverse, then the condition number of M inverse A is small, or we write M is close to LU form of A. M is close to an LU decomposition of A. It is not exact LU decomposition of A, because finding A inverse is difficult. Doing a LU decomposition of A will again require something like a basic direct solution method and take n cube number of steps. So, finding A inverse is difficult, finding LU decomposition of A is difficult. So, instead of LU decomposition of A, we find something which is close to LU decomposition of A, or we say ILU, incomplete. So, now if I can find out an incomplete LU decomposition of A, that is M inverse minus A inverse is not 0, but it is a small number. M is very close to A, and we multiply M inverse A, we in front of this equation we multiply M inverse here and M inverse here, we will see that M inverse A has a smaller condition number. So, when we will apply GMRES here, it will quickly solve the set of equations. That is the advantage of preconditioner. The other one is the multigrid method, which reduces the the spectral condition number of the iteration matrix, or which goes into the spectral space and improves the convergence property. We were discussing, if you go to present lecture, we are discussing about multigrid method. So, this is one sort of customization, that instead of solving x is equal to b, pre-multiply A with M inverse, or write, or there is something called right preconditioning also. If you go through the lectures, you will see that. So, that you improve the conditioning of the solution matrix, of the coefficient matrix. Instead of A, you make M inverse A your coefficient matrix, which has better condition number, and solve it. So, that will also help you to get faster solution. So, these type of techniques are there. I am again telling Amit, I am not sure about the term matrix solutions, how matrix solutions can be customized, this customization term, but certain modifications are possible over matrix solutions to get faster solution. And which matrix solution has to be chosen, that has to be decided over the size of the matrix, over the nature of the matrix, etc., and also depending on how much computing power you have. If you are working in an exam, you have given a 6 by 6 matrix to solve it, you are definitely not going to choose something like GMRES or something like conjugate gradient, because the calculations are pretty involved. But you can think something like a Jacobi method, where the calculations are simple and it can work out few steps. But if you have a very powerful computer and you are working with your computing speed, with a program which you already have developed, you are working with that, then you will choose preconditioned GMRES, and you are solving a large matrix, choose preconditioned GMRES and solve it in less number of steps than the steps Jacobi or Gauss-Seidel will take for that case. So, it depends on what is your application and what are you actually trying to do in that case. Okay, do we have any further questions? As I still cannot see any other question, how much time have we spent? Not gone for longer time, no? 20 spent. So, we have not spent, I can spend probably few more time on discussing certain issues. I will again try to start from the basic of iterative solvers, and we will see that conceptually if there is anything which can create a difficulty in understanding. So, we started with iterative solvers. If you remember, before iterative solvers we discussed about eigenvalues, symmetric positive definiteness of matrix, etc., because these are important when we are discussing the convergence of iterative solvers. So, we first took the Jacobi or Gauss-Seidel type of iterative solver. Okay. And we first getting some questions, I am looking into it, I will come back to it. So, we first took the Gauss-Seidel or Jacobi type of iterative solvers, which are, remember, restricted only for diagonal systems, diagonal equation systems, diagonally dominant, not diagonal, diagonally dominant equation systems. If the diagonal term is less than sum of the off diagonals, this matrix solver will fail. So, even if I have a matrix which in its row permuted form can give a diagonally dominant matrix, but it does not look like a diagonally dominant matrix, it will not work in Gauss-Seidel or Jacobi. Why? If we go back to the iteration matrix that we are getting out of Gauss-Seidel and Jacobi, it is required to have a spectral radius, that is the large modulus of the largest eigenvalue less than 1, and it does not remain so for a non-diagonally dominant matrix. So, the convergence of Gauss-Seidel and Jacobi is restricted by the spectral radius of the matrix, and it is only applicable for diagonally dominant or irreducibly diagonally dominant type of matrix. So, you can look into the definitions for these two things. So, if and also we have to increase the convergence of the iterative the spectral, we have to reduce the spectral radius of the iterative iteration matrix G in order to increase the convergence. So, we took a parameter which is called over relaxation factor and saw that the spectral radius of G reduced and we got faster convergence. So, successive over relaxation is a modification over the basic iterative methods to get faster convergence. However, still we cannot work for non-diagonally dominant matrix. We have no method specific to symmetric matrix, though symmetric matrices have certain nice properties. One nice property is that symmetric matrices will always have, real symmetric matrix will always have real eigenvalues, which means that if I go back to the iteration matrix, the iteration matrix will also have a real eigenvalue, will probably we can actually design a iteration matrix with a real eigenvalue, and the spectral radius can easily be calculated. There are few other advantages also, but Gauss-Seidel type of solvers do not take that advantage. So, we try to look into other type of solvers which can take non-diagonally dominant matrix, which can work better for symmetric matrices, and in which the convergence is not restricted due to by the nature of the matrix itself, that how is the spectral radius of the iteration matrix. So, we can further improve the convergence, and that is why we thought about projection based methods, but I will take, there are few questions, I will take few things for I will take those questions. One is Girish, can we take worksheets to solve the problems? You have to check with NPTEL office that whether they allow worksheets, but the question that is coming here does not need any extra table. I will see it even will not need any calculator, and there are very some calculations in certain questions you should be able to carry a sheet to rough sheet to work out that calculations. I think NPTEL will provide that, but you again post it as a question in the forum and we will check back to it. Kalpana, you asked me that please give an example. A transpose is equal to A. A is not a, so if A is not a symmetric matrix, okay, I think your question is different than what you wrote here. A transpose is equal to A. So, if I have, I take two examples, A11, A12, A21, A22, one example. I take its transpose, which is A11, A21, A12, A22. and all these are different numbers. So, of course, A is not equal to A transpose, because all these numbers are different. I have never said that they are equal. Now, I take transpose of this transpose. So, A11, A12, A21, A22 transposes A, and I take a transpose, which will mean transpose of this particular matrix, which is A11, A21, A12, A22's transpose. What will be it be? A11 will be here, A12 will come in the row, A21 will go in the second row, A22 will remain, which is same as A. So, A transpose is equal to A, but A transpose is not equal to A. So, if A is not a symmetric matrix, A transpose is not equal to A, but A transpose as transpose must always be equal to A for any matrix A. You can take any matrix and verify this. Okay. If A is symmetric, then A is equal to A transpose, as well as A transpose is equal to A transpose. So, if A is symmetric, if I am answering the Kalpana's question, I have A11, A12, this is also A12, A22. So, A transpose is equal to A11, this A12 will come here, A12, this A12 will go here, A22, which is equal to A. Okay. Kalpana, you also might look into the introductory chapters of Gilbert Strang's book when he is discussing symmetricity of matrix, and you will get few more examples there. Okay. Guru Vishwanathan referred the best book cover the lecture. As I started saying from my first class, that first part of this lecture, where I am only discussing the direct solvers, follows in with a great rigor Gilbert Strang's book on linear algebra. Okay. So, up to the symmetric definiteness of the matrix, etc., first 6 weeks, you can go through Gilbert Strang's book, and you can probably find that I am following almost chapter wise Gilbert Strang's book. And the second part, where we are discussing with iterative solvers, I am starting with I am again following Yusuf Sard's book on sparse method for linear what is the name of iterative methods for sparse systems, sparse matrices, Yusuf Sard's book. You go to my first lecture, I have shown these two books, and these are the all. You can also look into the portal where I have given these two as the textbooks, and these are the best books in this thing. If at least if you try to follow my lectures, I think only except few parts where I am trying to be more explicit to make it much clearer than the mathematical treatment, involved mathematical treatment they have done in their book. It is, except those things where I am trying to explain it in little more detail, it is exactly following these two books. For the direct solver part, for the first 6 weeks I am following Gilbert Strang, for the next 6 weeks we will mostly follow Yusuf Sard's book. And Golub's matrix computation book is also a reference book. There are a few good examples, and there is in certain cases, like for if you go for conjugate gradient solver, etc., he has a different way of explaining it. You can look into it, but these two books, Strang and Yusuf Sard, completes the course. Okay. Okay, so and so now I hope Kalpana's question is answered. So, I will go back to what we are discussing. So, then what we saw, that there is certain limitation of basic iterative techniques, and that is why we move to the next set of methods, where instead of solving x is equal to b, we pose it a problem of minimize x transpose Ax minus x transpose b. and if A is symmetric positive definite, then this minimization will give a solution of Ax is equal to B, and using this we developed a method called steepest descent, using this minimization technique. And then we have seen that what this is doing is basically minimizing a function, updating x. When minimizing the function, if we look into steepest descent method, it is starting with a guess value, updating the guess, assuming that the residual b minus ax is perpendicular to the previous residual, residual is perpendicular to something. So, this went on that idea that x new is equal to x old plus some value k, which is minimizing or with b minus ax new perpendicular to some space L. Once we look into steepest descent, we can see that from steepest descent these conditions can be put, and this is called a Galerkin condition. And then we exploited this condition to develop methods like minimum residual and residue norm. And first time we have seen that minimum residual needs only positive definite A. So, A may not be symmetric, may not be diagonally dominant also, only if A is positive definite minimum residual can work it, and residue norm works only for any non-singular A. So, any matrix can be considered to get, and that can give us this iterative method can give us a solution. So, we came out of the restrictions posed by basic iterative solvers like Jacobi Gauss cycle. These are called Jacobi Gauss cycle, SOR are called basic iterative methods. We came to projection based methods. This is called a projection based method. To design matrix solvers which can solve any non-singular matrix. Now, what is the problem restriction of this methods? When we have chosen the spaces k and L, x should be x new should be x old plus k, this is a one dimensional space. So, this is 1D vector added with another 1D vector. However, x new and x old, the final solution must be a member of row space, we have seen that earlier, and in our guess solution can be member of any space. So, I have to go from one particular vector space to another vector space to update the solutions, and adding 1D vector cannot be a very good way, because we may have to go, if we are in a real coordinate space Rn, we may have to go in n minus 1 dimensions to get the row space solution x new. So, the one dimensional k and L posed a problem, and we have seen that the number of iterations required for minimum residue and residue norm is very high. If we can, for diagonally dominant matrix, if we compare this with SOR, this is quite high. For symmetric matrix also, steepest descent is not better than a symmetric diagonally dominant SOR solver. So, we thought that we should modify these methods, and while modifying we considered this k and L, instead of being a one dimensional space, let they be n dimensional, and we introduced what is called Krylov subspace. So, if you go through the lectures, I have taken steepest descent as an example and saw that how from our initial guess the final till we reach the final x, how the guess value guess x is being updated, and we will see that x, which is the solution, say x star is equal to b, satisfies the equation. So, x star is equal to x 0 plus something into r plus something into a r plus alpha 1 r, alpha 0 r, alpha 1 a r plus alpha 2 a square r plus so on, plus alpha 3 a cube r plus it goes up to alpha n a n r, so on. So, a r is being multiplied with something and that is being added to the x 0. So, we can write that, I will probably go here. X 0 x star is equal to x 0 plus a space k m of a r, where k m a r is basically r plus a space spanned by the vectors r a r a square r, so on, till we get linearly independent vectors to span this, and this is called Krylov subspace. And based on the Krylov subspace, we have designed the algorithms like conjugate gradient, for symmetric positive definite A, GMRES for any A matrix. So, you should have been happy here. On top of that, we have observed that conjugate gradient is a very fast solver, because the convergence does not remain on radius, or condition number rather remains on square root of condition number. So, if condition number is 1.44, square root of condition number is 1.2 and the convergence is faster. GMRES is also a fast solver, and GMRES is applicable for any A. Conjugate gradient is not applicable for any A, it is only applicable for symmetric positive definite A. Problem with GMRES is that it is little mathematically complicated. It is also little complicated to write a computer program for GMRES, and it is difficult to identify where to stop, where the convergence has been achieved in GMRES. However, GMRES is a very good solver and widely used in practice. So, we thought that if something like conjugate gradient type of idea can be devised for non-symmetric matrices also, and we went to Langsos bi-orthogonalization and went to biconjugate gradient method. The problem with biconjugate gradient method has further been demonstrated that it does lot of operations in each iteration, though it takes less number of iterations. The number of operations in each iteration is quite high, and it deals with transpose of A, which can, finding out transpose of a matrix during iterations can pose certain problems in terms of how computer architecture and memory handling it. So, we modified biconjugate gradient and got a method called biconjugate gradient stabilized by CG stab, which is applicable for any matrix and poses convergence property very similar to conjugate gradient. In very less number of steps we can get convergence out of it. So, these are the matrix solvers, we have discussed it, and later we started discussing on preconditioning and multigrid methods. Is there any further question? Okay. Okay, so this is we'll see if we do not get any further question, we can probably wrap up for today. I believe that when we started Krylov subspace, even when we have started projection based methods, the mathematics is being little slightly abstract. You have to visualize lot of things, you have to work out few things on your own and try to see that how are these things connected. I tried to make it as simple as possible, but I am telling you that you go through any textbook, you will find that they are proposed in a very complicated manner. I will say you will take lot of time to understand that what are they trying to tell and how are the geometry, vectors, linear algebra or vector algebra, vector spaces and the iterative method are related in these cases. And on top of that also comes that how are the computer architecture going to work on it, what will be the computational complexity when you program it. So, these complexities makes this particular course little difficult to understand unless you try to work it out. But in case you are faced with some problems, especially from the Krylov subspace part, you always should write back to us in the feedback, in the forum, in the ask a question, through the ask a question in your NPTEL portal forum, and I will try to answer it as much as possible. I will hope that we should also once come for a live session before your exams, that is maybe 3rd week of the October. before you have your exam, so that you can come with more doubts, and we can address that. And we'll by that time we'll start parallel computing block matrix algorithm, as well as preconditioners and GMRES, which preconditioners and multigrid, which will be for multigrid. I will give you just an introduction, will not really go into a detail, because it is again a much developed and much larger part of mathematics is involved in multigrid method. Will not go into the detail. I will try to give you some introduction here. Another idea is that because you are getting introduced with several solvers and several terminologies regarding the solvers, you will find in online open source resources lot of solvers are available. So, you can download it and try to use it yourself and do some numerical experiments on that. If you are not writing your own solver, you can write it in any computer language, but if you are not writing, you can also download this from internet resources. If search with BiCG step, you will find out many BiCG step programs, executables, as well as source codes. You can try with different matrices and see how they are working. And remember, these matrix solvers like BiCG step, like conjugate gradient, they are designed for large matrices. If you take a 3 by 3 matrix, there is not much advantage in solving it using BiCG step or GMRES. But if you have a 3000 by 3000 matrix, you can readily see that how fast is BiCG step compared to Gauss-Seidel or Gauss elimination or LU decomposition. So, for large matrices, and the route to generate large matrices I have discussed with you is, one is finite difference method, another is finite element method. These two things I have briefly discussed with you. With that, you can generate large matrices and try doing this numerical experiment with the solvers you can get from online resources. Okay, Girish, the difficulty level of questions appear in the exam. It will be definitely similar to the assignments. I tried to keep it as simple as possible. I understand that the concepts are not very simple. So, there will be difficulty, but if you go through the slides meticulously, you should be able to answer most of the questions. You really do not need to remember formula. You just work out the assignments yourself and work out the derivations we have done during the lectures in the slides. That should be sufficient to prepare for the exam. The questions are not very difficult. Some of the questions are actually very simple, which tests your understanding, but what is important is that whether you have the right understanding. For example, if I talk about conjugate gradient, you should be able to recognize that it is applicable only for symmetric positive definite matrix. If I talk about a eigenvector, you should be able to identify that this comes as the null space of A minus lambda I. This understanding will be required. If you go through the slides, I think whatever I have discussed in the slides, at least whatever I have asserted during the discussions, those are the points from where the questions are set. So, you can prepare well just by going through the slides. Iterative methods is complicated, so give more questions with yes, Guru Vishwanathan. I understand that this iterative method for linear system is complicated. We are giving 10 questions every week on iterative methods, but I will see that if I can maybe before by the third week, if I can upload a document on some practice questions on the iterative methods, especially the projection based method and Krylov subspace methods. So, at least you can have some more thing to practice, but again I am telling, if you work out the assignments and if you try to go through the slides, you will be it will be good for exam purpose, also for the purpose of understanding. Another thing you also can try to do is that you take, like for lecture 42 to 43 to 45, this one slide which title lecture 43 to 45. If you take this particular slide and see that what can be the questions from the slide itself. Remember, this is a multiple choice or true false type of question. The question that will be asked will be checked by computer. So, this will be short questions with very precise answers. So, if you try to figure out what can be asked from this particular slide, you probably will build your own question bank. I will try to give you something more for practice, but that will take me to take me another 10-15 days, but not 15 days will not be good for you, but maybe another 10 days before your exam I will try to give you something. Okay. Okay, any further question, or should we conclude the session? Okay, so thank you all for coming up with nice questions in the live session. You have any further question, you can always write to me. If I see the question requires more deliberation, I will answer back in writing, or I can ask you to email me and write in my. You can email me. You will find my email ID from the portal. You can always email me if you have a question which you cannot write in the forum, which is a large question with lot of mathematical expressions, etc. But yeah, thank you all for this live session. Prepare well for the exam, and more than the exam, it's important that how are you understanding the concept. So prepare your understanding better, and give the course its the required time, and try to work out all the mathematical steps which has been shown to you in the slides. Okay, thank you all.